I'd like to show you how to use integration to derive the constant acceleration kinematics equations that you're already familiar with for an object moving in 1D. So suppose our object moves with constant acceleration a with position x naught and velocity v naught at time t naught. So we're given some initial position and initial velocity at this initial time. I'll kind of structure this to follow along through our 5-step procedure here for setting up and solving integrals. So we'll start with the statement of a derivative. This is our starting point. We know acceleration is constant. That's our premise here. So acceleration is constant. Acceleration is dv dt. Next step, rearrange that derivative into two integrals. Move the dt over. So we have dv equals a dt, and then add up an infinite number of these infinitely small quantities on each side. Step 3 is where we set our upper and lower limits of integration. So in this case, what we want is to find the velocity as a function of time. So we'll note that given our initial conditions up here at time t naught, so when our independent variable here, t, has its initial value t naught, at that same moment, this independent variable v has value v naught. Okay, so t naught and v naught match, and those are our starting conditions. Our upper limit here, our independent variable t will have some future value t, when our independent variable here v has this future value v of t. So t naught to t and v naught to v. The lower limits match and the upper limits match. Step 4 is to find our antiderivatives. And let's note on the left-hand side that there's always a little 1 sitting in here as our hidden integrand. So the antiderivative of 1 with respect to v is v plus some constant c. And on the right-hand side, a is just a constant, so it could be a number like 7. So we're integrating this constant with respect to time. The antiderivative is a times t plus some other constant, c prime. Step 5, that's where we evaluate. We show that we're going to evaluate our antiderivatives with this bracket notation at the initial and final values of our limits. So v plus c evaluated from v naught to v, and this evaluated from t naught to t. What we mean there is that we're going to substitute in v for v, and then substitute in v naught for v, and take the difference between the two. We know our constant is going to cancel out right away. So this becomes v of t minus v naught. And on this side, t is going in for the independent variable t. T goes in for t, so we have at, and then t naught goes in for t. So at minus at naught, and the c primes cancel. So there we have it, the first constant acceleration equation. I can move the v naught over to the right-hand side, and we get this form here, or leave it in like these delta forms. So this is delta v over here equals a times delta t over here once we factor an a out of that side. That's our first equation. We take this and we integrate again to get the second constant acceleration equation. So we've got the velocity as a function of time. We now note as our new starting point that the velocity, the instantaneous velocity, equals dx dt. So we start by stating this derivative relationship. And maybe before we continue on here, I would like to take a moment to go back and note what are the key steps here that you should have on the page to show your work. You always include this. You start with your derivative relationship. The next thing you must have on the page is this, rearranged into an integral with the upper and lower limits indicated. And the next thing you can have is this here, the antiderivatives in the brackets with your lower and upper limits indicated. And then you should show the substitution step and, of course, your answer as well. So I guess I'm saying you can kind of skip this intermediate step here on the page and skip this intermediate step here on the page. Those in pink brackets are what are essential. Okay, so here, v of t equals dx dt. We're going to rearrange that into two integrals. So multiply both sides by dt, move the dt over, so it's dx equals v dt. Integrate both sides, meaning add up an infinite number of these infinitely small things. Set your limits now. Okay, so when time has value t naught, x has value x naught. So x naught and t naught, these match. Those are your lower limits. I'm going to go to some future time t when x has this future value x of t. So we've got our limits matching, and you'll note here how I've substituted in for our integrand here and for our velocity function the first constant acceleration equation. This I subbed in for our velocity as a function of time to get our integrand here. Okay, find the antiderivatives on both sides is our next step. On the left-hand side, there's a little 1 sitting in here. That's our invisible integrand, so 1 dx. The antiderivative of 1 with respect to x is x plus c. And on this side, let's note that we have our independent variable t appearing right there. Everything else inside here is a constant. V naught is a constant, A is a constant, A is a constant, and T naught is a constant. That's just some specific starting time. So only that time there, that's the only appearance of our independent variable t. So in finding our antiderivative, we treat these other things as constants. So the first term becomes V naught t. There's our variable. Then the AT term becomes a 1/2 AT squared. The AT naught term becomes AT naught t. Note how t naught is a constant, and it picked up a factor of t, our variable, and then we add some other constant. Okay, there's our antiderivatives. Step 5, we show that the result of integrating is that we're going to evaluate our antiderivatives at the final and initial values of our independent variables. That's this bracket notation. So x plus c from x naught to x of t, and then this antiderivative evaluated from t naught to t. We know that the c's are going to cancel out right away, so you don't even have to write in those c's there. It's not necessary. All right, I'm going to go to the next page. Let's finish evaluating this here. Excuse me. Okay, so I've just rewritten that step, and then we should show our substitutions. So this step should be indicated on your page, and then this whole step should be indicated. What we're doing here is plugging in x for x and then x naught for x and subtracting. So x of t minus x naught, that's the left-hand side. Then on the right-hand side, once again, our variable t is here, here, and here. The t naught is a constant, the a is a constant. So these are going in for the t's. So t goes in for t here, here, and here to give us this expression. Then minus the antiderivative evaluated with t naught going in for t, t, and t. So t naught is going in there, there, and there to give us this expression. V naught t naught plus 1/2 a t naught squared minus a t naught times t naught, so a t naught squared. So we've got some simplification to do on the right-hand side. Let's see. I'll note that I've got a v naught t term and a v naught t naught term. I'm going to combine those terms to give us this term right here. I also see that here we go. 1/2 a t naught squared minus a t naught squared gives us negative 1/2 a t naught squared. There's a minus out front of that, so those combined give us this term. And then here are the remaining two terms carried down. Okay, I'm going to simplify that another step by factoring out a 1/2 a from this term, and this term. Factor out that 1/2 a. That's going to put a 2 here when I factor out the 1/2 a. So that gives us this. And then I note that this thing in parentheses is equivalent to t minus t naught squared expanded outwards. And there we have it. If I just move the x naught here over to the right-hand side, then we have x of t equals x naught plus v naught t minus t naught plus 1/2 a times the quantity t minus t naught squared, or in terms of deltas, delta x, a delta t here, a delta t there. There's our constant acceleration equation number 2. Let's see here. To get the third equation, no calculus is necessary. We're just going to eliminate the delta t between equations 1 and 2. So I'm going to take equation 2 here. I'm going to take this equation. I'm going to multiply the whole thing through by 2a. So 2a, 2a, and 2a, making it look like this. So 2a delta x, 2a v naught delta t, 2 and the 1/2 cancel, and we get an a squared times delta t squared. So I've just transformed that equation into here, and now I'm going to plug in this, substitute delta v for a delta t. All the a delta t is going to get replaced with delta v's. So this a delta t gets replaced with delta v, and this a delta t gets replaced with delta v. So that becomes 2v naught delta v plus, this is a delta t whole thing squared, so delta v whole thing squared. Delta v is v minus v naught, final minus initial, and then it's final minus initial, the whole thing getting squared here. So check my algebra a few steps, multiply that out, combine some terms, and it simplifies down to this. Ends up with just v final squared minus v initial squared. So there's our third constant acceleration equation. V final squared equals v initial squared plus 2a times x final minus x initial. Or in terms of deltas, change in v squared equals 2a times the change in x. This term is often mishandled, so note that common mistake here. The change in v squared is not the same thing as the change in v quantity squared. This mistake is often made. I'll remind you that a delta of a thing means the final value of the thing minus the initial value of the thing. So change in v squared actually means the final value of v squared minus the initial value of v squared. So this is what it actually means. It does not equal this stuff on the right. It's often mistaken for the change in v squared, but we know that would mean the final minus the initial quantity squared, multiply it out, and we get this. And you can see this is clearly not the same thing as this. So avoid that mistake. This is the correct expression that's appearing right here. V final squared minus the initial squared. Okay, that's our third one. And the fourth constant acceleration equation, which is very handy but often overlooked, is the one that comes from our definition of average velocity, integral over interval, delta x over delta t. We already performed this integral, integrated v dt to get a constant acceleration equation number 2. So we've got this expression for delta x. So let's see what happens when we utilize that. So our average velocity, delta x over delta t. In for delta x, I'm going to sub in our second constant acceleration equation here. You recognize it, the numerator, v naught delta t plus 1/2 a delta t squared. So I've plugged that in, and I can factor out a delta t from the numerator. So this is a delta t factored out times the quantity v naught plus 1/2 a delta t all over delta t. And then I can cancel out a delta t since I was able to first factor it out. Okay, that gives us just that left. And at this point, I'm going to plug in the first constant acceleration equation. And for this a delta t, I'm going to plug in delta v. That's the first equation. So delta v there. Delta v meaning v final minus v initial. So v naught plus 1/2 v final minus 1/2 v initial. V initial minus 1/2 v initial gives us 1/2 v initial, so that gives us this. This simplifies down to half of v final plus v initial, or the mean of the initial and final velocities. So this is the one occasion when this expression actually does give you the average velocity, because here our velocity function is linear with time if acceleration is constant. Let's go back to see that explicitly. Here we go. We found that if the acceleration is constant, then our velocity is a linear function of time. So in this one and only this one special case is average velocity actually given by this expression here. This is the special case. So in this form, we say the average velocity is delta x over delta t equals the mean of the initial and final velocities. Often a handy way to express this would be to say delta x equals 1/2 the final plus the initial delta t. It's often useful in this form because note this is the only one of our 4 equations in which acceleration actually does not appear. So it's useful if you don't know the acceleration and you're not trying to find the acceleration.